Hello friends, this is Mechanical Vibration, lecture 10, the first part of lecture 10. It is about 2-degree of freedom system. So it is all about the vibration of 2-degree of freedom system. So the learning objective of this chapter, especially 2-degree of freedom system, is to formulate the equation of motion of 2-degree of freedom system, to identify the mass, the stiffness, and the damping coefficient matrices for the equation of motion, to compute the natural frequencies of vibration and the mood shapes. That means to compute the eigenvalues and the eigenvectors of the system, and to determine free vibration solution using the known initial conditions. There should be some prescribed initial conditions. So implementing those initial conditions, we will determine the free vibration solution. To understand the concept of coordinate coupling and the principal coordinates. So this is another part of the discussion. To understand the concept of self-excitation and the stability of the system, and to use the Laplace transform approach for solution of 2-degree of freedom system, and finally to solve 2-degree of freedom free and forced vibration problems, and to implement these equations to the MATLAB code in order to plot some of the vibration problems. So these are the objective of this topic. So when we say 2-degree of freedom system, we are talking about the number of independent coordinates that should be described. So in our case, in the case of 2-degree of freedom, the coordinates or the number of independent coordinates or the number of independent systems that should be described is 2. So for any number of degree of freedom system, we have any number of equations are required. So the any number of linear algebraic equations will be required. So in our case, for 2-degree of freedom system, we have 2 independent coordinates and 2 equations of motion. Some of the examples are, for example, the automobile system. We can see here automobile system. How we can simplify this automobile system as a 2-degree of freedom motion. We can model it as the suspension system of the car as a spring, and the total mass of the car, considering the central point or the CG or center of gravity of the system. Sorry, there is some call. Anyways, okay, so taking CG as the point where all the vibration will take place. So on that, we consider the motion to the front side and motion to the back side of the car as kind of degree of freedom, or we can represent it in terms of the rotational motion of the center, as well as the linear motion of the reference point, CG point. So, for example, look, we have this line, that line AB, represented like this. Then the motion of this point, CG point, from here to here is taken as x of t. That means the displacement at time t. And at the same time, the car system will make a rotational motion, which makes theta angle. So as we see, about the reference line, it makes theta angle here. So we consider this. So these are expressed in terms of x and the theta. So that is taken as a 2-degree of freedom motion here. Okay, let's consider the lathe machine. The lathe machine is a simplified diagram of lathe machine is this. that shows headstock, tailstock, live center, dead center. So the workpiece will be placed in between here, and the cutter and the carriage are also sliding over this bed. So bed is the structure. So this is a simple representation of lathe machine. As we know from mechanical, the use of lathe machine is to produce circular profile of workpiece. So, and also some other geometries. So this lathe machine also represented or modeled for the vibration analysis. The whole, it is represented as the column. The stand for lathe is considered as short column, and the bed, the lathe bed is represented as a beam, okay, a vertical structure called beam and column. So the column stiffness to this direction represented as K1, and the backside towards to the tailstock is K2. And the center, or the center of mass, or the center of gravity is taken at this point. Then it will vibrate about this point, like as we have seen here. So x of t is there. So we can also represent two coordinates like x1 and x2. Means the node A to A prime taken as x1, and the node from B to B prime is taken as x2. On that, we can also represent this lathe bed. Okay. This is also another 2 degree of freedom system that contains instruments, and it is cushioning system. So this is the instrument which is expected to be protected from impact or any kind of impulsive load. And there are a cushion materials which protects the instrument. The suspicious instruments will be protected from it is external load. So this is the cushion materials or the packaging material. So we simplify it as like this. The instrument as one of the mass, the cushion material from this direction and this direction, we consider K1 here. And here we consider K2. So we have a motion of this thing towards to this direction and this direction. At the same time, the Y motion also there. This most of the time works in kind of seismographic kind of modeling. Okay, so this is another model also, and this is packaging material for the instruments. This is also a representation of some mechanical system, especially in complex machining tools. We have this type of structures. So this structure is represented as a 2 degree freedom system. Okay, so here it is constrained at this point, and various damping systems and spring elastic constants are represented here, and mass, the lumped system of the whole mass taken as this. Again, here the mass is taken, so we can represent like this. Again, we have 2 degree of freedom system of torsional system, having flywheel and shaft. So we have discs and shafts, which are subjected to some torque and creating θ1. For disc 1, it produced θ1 that resulted from forcing or the torque MT1. And also for shaft 2, which is characterized by the moment of inertia J2. Okay, so the torsional J2. So, and the shafts are considered as the elastic material KT1, the torsional stiffness KT1 and KT2, KT3 here inside. And also here, this is a cantilever form of, this is both in fixed shaft and this is one in free and one in fixed shaft. So we can represent 2 degree of freedom. So when we talk about degree of freedom, we must consider the number of masses. And in most cases, we consider discrete mass or lumped mass on the system. So this is 2 degree of freedom system. So number of degree of freedom indicates that it is a minimum number of independent variables to define the position or motion of the system. And it is known also known by the mobility. Okay, the general rule for competitions of the number of degree of freedom can be NDOF, which is equals to number of masses in the system times number of possible motions of each mass. So this is the simple formula to calculate the number of degree of freedom in the system. So in general, we have for 3D objects, we have 6 degree of freedom. These are 3 translational degree of freedom plus 3 rotational degree of freedom. So the 3 translational degree of freedom are the translation about x-axis, that is just like this, the translation in the z-axis, translation in the y-axis. So these are 3 degree of freedom for a 3D object in the space. And there is also rotational degree of rotation about x-axis, rotation about y-axis, and z-axis. So rotation about x-axis is called pitching motion. Okay, the rotation about x-axis is pitching. And the rotation about y-axis is the yaw motion. The motion is called the yaw. We can easily identify the airplane which is flying in the space. So the airplane can make pitching, that means nose up and down motion is called pitching. And the airplane which rolls about its axis, rolling motion means like this. And the yaw motion means just moving motion like this. Okay, that is yaw motion. So 3 rotational degree of freedoms are the pitch, yaw, and the roll. And the 3 translational motions are back and front motion, down and up motion, and also right and the left motion. So these are the 6 degree of freedom motion. Okay. So vibration analysis of 2 degree of, let's directly come to the vibration analysis. So on that, we already specified the laser machine. So that laser machine a simplified analysis will be carried out for the laser machine here. Okay, the displacement of the laser machine about CG is represented by x of t, and it is rotation represented by theta of t. Or so we can use x of t and theta of t, or someone can use x1 of t, that is the displacement of node A, and x2 of t, that is the displacement of node B on the laser machine here. Okay, so we can do that. So by a 2 degree of freedom system that requires 2 independent coordinates to completely describe the equation of motion. So the coordinates are called generalized coordinates. Okay, when they are independent of each other. So they are generally in the form of coupled differential equation. These 2 equations are coupled differential equation. The differential equation in terms of theta and the differential equation in terms of x are the coupled differential equations. Or someone expresses them in terms of x1 of t and x2 of t for the motion of 2 nodes. Then still we can get 2 coupled differential equations. Okay. So for that, we may consider harmonic solution, or we can consider differential equations like e raised to. So different it depends on the type of equations what we have. And whenever we apply suitable initial conditions and suitable excitations to the system, then we can find the system will vibrate at one of its natural frequency. So for 2-degree of freedom motion, we have two natural frequencies. One is the smallest natural frequency, on that is the one which we start to design or understand carefully. So during free vibration at one of the natural frequencies, the amplitude of coordinates are related in a specific manner, and the configurations is called normal modes. So we have normal modes that are the vibration modes. Okay, maybe our system vibrate in the same direction with the same amplitude, or the system might vibrate with the same magnitude with opposite direction. So that gives us the mood shapes. Okay. Okay. So for 2-degree of freedom, we have two normal modes. We can see this thing immediately after some example. Okay. So let's see this this system. Most of the time, people use a general form of 2-degree of freedom system. This thing. So this thing consists K1 C1 M1, again K2 C2 M2, and bosons are fixed. So this helps us to generalize. Okay, the thing should not be exactly this, but we can generalize from this. And sometimes if it is not the undamped one, then this C1 and C2, C3 will be given 0. Then the equation of motion will be vary. But we can directly take this equation of motion and we resolve, or we remove, or we neglect the thing which is not there. Or sometimes this M2 is free from constraint in this direction, so that we can give 0 for this condition. Okay, so this is the general form of 2-degree of freedom motion in the linear form. So for this, the free body diagram of the system is given like this. Mass 1 is expected to move in this direction. So F1, X1, X1 acceleration and displacement of mass 1. Acceleration and displacement of mass 2 is given here. So we cut the system here, then we can get free body diagram. So from this side, K1, X1, C1, X dot 1. So here also, X2 minus X1. When we consider M2 is displacing towards to the this point, so the displacement of X2 is greater than X1, so that X2 minus X1. Okay, that is relative deflection or displacement between M1 and M2 is X2 minus X1. So the motion of the system is completely described by the coordinate X1 of T and X2 of T. So X1 of T, X2 of T, which define the position of the mass M1 and M2 at any time T for the respective equilibrium position. The external forces, the excitation forces, are given as F1 and F2 of T, okay, that act on the mass 1 and the mass 2. And the free body diagram given here. So the application of Newton's second law yields us the equation of motion. Look here, just looking the free body diagram, we consider spring. K1 is intention. K1 intention means what? This mass is applied to this direction. Again, K3 is intention means still this mass also moving in this direction. No, compression means M2 is moving against K3. Okay, so that means this system is in tension. Spring K2 is in tension means the relative displacement x2 minus x1 is positive. Okay, this relative displacement x2 minus x1 is a positive difference. That delta is positive means the system, inner system is so the whole system is moving towards to the surd stiffness. So K3 is in compression. That means mass 2 is pushing K3. So from that assumptions, okay, maybe in the reality it may be in opposite direction. Okay, actually it is not, but we can see the forces here. So these forces produce this reality only. So this gives us two differential equations in terms of x1 and x2 and the m1 and the m2. So for this system, means the first system, system A, m1 x1 t plus c1 plus c2 x1 t minus c2 x2 of t plus k1 plus k2 x1 of t minus k2 x2 of t, which is equal to f1 of t. In similar way, for this free body diagram, for this part, for mass 2, the summation of force in z x is equals to 0 gives us this equation. So these two equations are two coupled differential, second order differential equations. We can expect that the motion of m1 will influence the motion of m2 and vice versa. So two masses are influencing each other so that they are coupled. So in matrix form, the above representations, the two equations given above are represented in matrix form M times, okay, M is a diagonal matrix, M1 and M2 shows the lumped masses in diagonal of the this thing. Sorry, there is 0 here, M1, 0, 0, M2. Okay. Again here, yeah, here also 0 is there because there is no mass for these diagonals. Okay, so these are the representations. Okay. C represents C1 plus C2 minus C2 minus C2 C2 plus C3. Okay, K1 plus K2 minus K2 minus K2 K2 plus K3. This is K2. Okay, don't forget this is K2. Okay, and here x is represented the vector x1 of t and x2 of t. If this f of t is equals to f1 of t, okay, so these are force vector and displacement vectors. Okay, the solution to the equation of motion. So that for the above equations, equation of motion 1 and 2 become uncoupled only when C2 is equal to K2 is equals to 0. This C2 is equal to K2 is equal to 0 means there is no connection between one of the system to the another system. Means the link is uncoupled or independent of one another. Okay. Which implies that two masses are not physically connected. Means this condition represents here there is no connection, means K2 0, C2 0. That means this mass is alone, another mass is alone. So one cannot influence another. But whenever this connection is there, they are influencing each other. M1 influence M2, M2 influence M1. That is the meaning. Okay. In such case, the matrix MC and the K become diagonal matrix. The solution of question 1 and 2 for any arbitrary force F1 and F2 of T is difficult to obtain, mainly due to the coupling of the variables x1 of T and x2 of T. Here it is also x2. The solution of equation of motion involves four constants. What are these four constants? Let's see. One of the constant is x1 of t, x2 of t. Another constant four constants. Yeah, the derivative of x1 and x2 also are another unknowns. So we need four initial conditions. Okay? In order to solve this, we need four initial conditions. These are two from the displacement initial conditions and two from the velocity condition. Okay? Therefore, it is better to consider the free vibration solution of equation 1 and 2. Let's leave the forcing function case first, and let's consider the free vibration analysis. Okay? In the case of free vibration, there is no external force. So, for example, we can take this example. Okay, the free vibration analysis. There is no damper. Okay, we have only K1 and the K2, M1 and M2. So X1, X2 are given here. K3 is here. So in this case, what we can do, all the damping constants are zero. All the force vectors are zero. So our final equation from equation number 1 and the 2, we can get this one. So just substituting or neglecting these things. Okay, so this is free vibration. The solution for free vibration for the two equations given above, x1 of t, assuming just a harmonic solution, x1 of t is equal to x1 cos omega t plus pi, x2 of t is equal to x2 cos omega t plus pi. Here we can simply say xi means just to. So here x1 and x2 are constants that denote the maximum amplitude of x1 and x2. And pi is the phase angle. So substituting equation here still I'm making some mistake. Mistakes are there. Let me write those things. This is x2. This is also x2. Let me go back once. There are some mistakes which I have seen here. Here it is 0. Here it is 0. This is K2. Okay. Yeah, here it is K2. K2. So x1 of t is equal to 0 is equal to x1 naught. X2 of t is equal to 0, x2 of 0. X1 dot of t is equals to x1 dot of 0. And x2 dot of t is equal to 0 is equal to x2 dot of 0. So these are the four initial conditions what we have in order to determine the equation or the four constants. So here, two equation of motions are developed from equation number 1 and 2. Just this giving 0 for C1 is equals to 0. C2 is equals to 0. C3 is equals to 0. And also F1 is equals to 0. F2 is equals to 0. F2 is equals to 0. We have only x1 dot dot x2 dot dot. So taking this equation and assuming harmonic solution, just a simple harmonic solution for m1 and m2 x1 of t, which is called x1 cos omega t pi 1, we can put pi 1. Okay, this is pi 2. That's why four constants. X1 is unknown, x2 is unknown, pi 1 is unknown, pi 2 is unknown. So just assuming this solution to the previous solution equation of differential equation, we can get this equation. Okay. This equation provides us the characteristic equation. Okay, so this is equal to 0 means we consider the quantity inside of square brackets here. So considering those things, we can find the characteristic equation. Okay. So how we can find the characteristic equation? Yeah, this is general form of equation in the matrix form. So this equation represents two simultaneous equations with algebraic equations with unknown x1 and x2. For non-trivial solution, the determinant of this quantity, is equals to 0. So from that, we can find the characteristic equation. So this is a characteristic equation that we obtain from these times this quantity times this quantity minus this quantity minus this quantity. So which gives us the characteristic equation. And from this characteristic equation or frequency equation, we can obtain the two natural frequencies, means the characteristic values. Now we can find the characteristic values, yeah, using the two quadratic formulas in terms of omega square. Okay, the first and the second natural frequencies, which is equals to this equation. Means from, as we know, x is equals to minus b plus or minus radical of b square minus 4ac. 4ac is whole over 2a is our quadratic equation. So our x is in square form now. So x1 and 2 is this equation. Okay. From that, we can obtain omega 1 and omega 2, which are natural frequency of the system. And these values of x1 and x2 depend on the natural frequency, this omega 1 and omega 2. Just for the first mode of omega 1, I is equals to 1. Okay, this in general form, but for omega is equals to 1, we substitute omega 1 value from this equation. Okay, again, for omega 2, we substitute omega 2 values in direct equation of this. So then, for this, defining the amplitude ratio, that means x2 over x1, what we have is minus m1 omega 1 square plus k1 plus k2 over k2, which is equal to k2 over, means this is from the second equation, this is from the first equation. So we can use only one, that is sufficient. Whether we use this one or this one, it gives the same value. Again, similarly for omega 2, just substituting for the equations in omega 2, then we can find the amplitude ratio R2 of second mode. This thing implies second mode. This thing implies first mode. So just observing R1 and R2. So in our case, in the first mode, R1 and R2 are identical. That means X2 is equal to X Ri times X1 for I1 and the 2. So the normal modes of vibration or normal vectors, these are the normal vectors, okay? Or we call these are eigenvectors, okay? These are the eigenvectors in the first mode, and this is the eigenvector in the second mode, okay? So we can represent in this manner. Finally, the free vibration solution, just substituting these equations to here, we can obtain the free vibration equation. So x1 cos omega 1 t plus pi 1, okay, x2, here it is x2, sorry. No, in the first mode it is 1, okay. In second mode it is 2. x2 of 2, x1 of 2 of t, x2 of 2 of t. So these two second mode. So which gives our x1 cos omega 2t plus pi 2. Amplitude ratio R2, x1 of second mode cos omega 2t plus 5. So this is the free vibration solution. Now we have here 4 unknowns in the above equation. One unknown is this one. We don't know exactly this value. Second unknown is this value. Okay. The third unknown is this value. And the fourth unknown is this phi 2. X1 of the first mode, phi 1 means the phase difference in the first mode. X1, the amplitude of maximum amplitude of vibration in the second mode, pi 2, the phase difference in the second mode. These are unknown. So we have to determine this using initial conditions. So what are the initial conditions we have? X1 of t, which is xi of 1, which is constant. So we apply this initial condition in general in order to determine. And then finally, we superimpose the equation of motion of xi of 1 and x of 2, second mode and first mode. So this is called a superposition. So what we can get then, just considering C1 and C2 1 for no loss of generality. So here, just consider this as 1. Again, this C2 as 1. Just assuming no loss. So this equation becomes x of t is equal to x of the first mode plus x2 of the second mode of t. Okay, so in this context, what we can do, x1 of the first mode, x2 of x1 both in the first mode and the second mode. So just considering x1 component of the first and the second mode, we have this equation. Okay, omega 1t plus pi 1 plus cos omega 2t plus pi 2 for the first component of x1. x1 in the first mode, x1 in the second mode. So again, for x2, we consider considering the amplitude ratio for the first mode, x1. This means actually this is x2. This is x2. x2 in the first mode. This is also x2 in the second mode. Okay, so just substituting this thing, we can get these two equations. This is the second algebraic equation. No, second solution. Now we can find these constants. How we can find? Just assume this initial condition. Assuming this initial condition, x1 of 0 is equals to x1 of 1 cos pi 1 plus x1 of 2 cos pi 2. Just use this equation on this equation, substitute 0 here, substitute 0 here. Again, the first derivative of this will be x1 dot of 0. Substitute it. What you can get is this equation. Again, x2 of 0. That is, we can get this equation. x2 of 0. Substituting 0 here, we can get this equation, and the derivative of x2 of 0. Derivating this one, we can get and this equation. So on that equation, this is the final. So these are the application of initial conditions. So the 4 algebraic questions what we have here are from the previous slide. R1 x1 of 0, x1 or 1 cos pi 1 is equals to amplitude ratio R1 x1 of 0 minus x2 of 0 over R2 minus R1. x1 of 2 cos pi 2 is equals to minus R1 x1 of 0 plus x2 0 over R2 R1. x1 of 1 sin pi, the derivative part, which is equal to minus R2 x1 dot of 0 plus x dot 2 of 0 over omega 1 times R2 minus R1. And x1 of the second mode, sin pi 2 is equals to R1 x1 dot of 0 minus x2 dot 0 over omega 2 R2. So again, using these 4 equations, we have this kind of relations. x1, directly x1 means x1 cos pi 1 square plus x1 of 1 sin pi 1. So x1 square will come out. So cos square pi 1 sin square pi 1, it is 1. So that this is simply x1. So that means just substitute from this equation. Sorry, back. Substitute instead of x1 cos pi 1, substitute this. And x1 of 1 sin pi 1, substitute this one. Okay, that means this equation. So this equation finally gives us this type of expression. Okay. Similarly, for the second mode, x1 of the second mode cos pi 2 square plus x1 of the second mode sin pi 2 square, which simply gives x1 of 2, which is by substituting this term, finally we get this equation. So that is one equation, equation 1, equation 2. Because we have 4 unknowns, then we are determining the 4 unknowns. Okay, so pi 1 is tan inverse of this quantity. So tan inverse of this quantities, we get pi 1. This is pi 2, sorry, pi 2, tan inverse of the second mode term, sin pi 2, cos pi 2. So we have 4 unknowns. Now we got all 4 here. Okay. These are the 4 constants. So some example on free vibration. Just taking a simple example. Okay, example of free vibration. So find the natural frequency and mode shape of the spring mass system shown in figure 6. This is our figure 6, 2 degree of freedom system, having K1 is equal to 2, K2 is equals to n times K. So for n is equals to 1, it also K, and K3 is equal to K. All of them are K. And the motion of M1 is considered x1 of t, the motion of M2, x2 of t. So the vibration equation of motion is this and this, the 2 motion of equation from equilibrium condition. So this equation simplified by substituting with k terms, we get mx1 dot of t plus 2kx1 minus kx2, which is equal to 0, mx2 plus 2 times x2 minus kx1 is equal to 0. So these are the two equations. Now, by assuming harmonic solution like this, xi of t is equal to xi cos omega t pi, we substitute that harmonic equation into the solution. Finally, we can get the this type of equation. So here it is not simply like this, but determinant of this equation is equals to 0, which gives us the characteristic equation. This is our characteristic equation. The determinant of the thing inside the bracket is this. Finally, the quadratic roots of omega are obtained like this. So our omega 1 is equals to radical of k over m, and omega 2 is equal to radical of 3k over m. By simplifying this, we can finally get this equation. So once we get omega 1 and omega 2, okay, so we can find the amplitude ratio. So amplitude ratio R1, which is equal to x2 of 1 over x1 of 1 first mode, which is equal to minus of m omega 1 square plus 2k over k, or which is equals to, in the first mode, yeah, omega 1 means omega 1 square means k over m, so we substitute k over m plus 2. So if we cancel m by this m, we have left minus k. Minus k plus 2k means we have k. K over k is equals to 1. Okay? So this implies both masses m1 and m2 are oscillating in phase with equal amplitude. The amplitude is also the same. Okay, their phase is also the same. So that means if this is m1, if this is m2, these masses are vibrating in the same, they are in the same phase, okay, and having the same amplitude. Okay. Another case, R2 x for the second natural frequency, we substitute instead of omega 2 in the omega 1, omega 2. So 3k over m minus m. So here we cancel m by m. We have left 3k plus 2k minus 3k plus 2k minus k. So minus k over k gives us minus 1. This minus implies masses are oscillating in 180 degrees out of phase with equal amplitude. Okay, so in this case, pi is equals to 0, and they are in phase, and here pi is equals to 180. 180 degrees. Okay. So our natural modes of vibrations in first mode and in second mode are given like this. So x1 of 1 of t is equal to x1 of the first mode cos radical of k over nt plus pi 1. x2 of t, which is equal to x1 of 1, means we have only 1 here. Okay. So this is the solution, and this is also solution for second mode of vibration. So how we can represent? Look, this is the representation. In the first case, these are the two masses which are displaced some x amplitude like this. So both are in phase. So look, m1, this is m1 and this is m2. So if m1 is moving in this direction, m2 also moving in this direction with the same amplitude. Or if M1 is moving in this direction, M2 also move in this direction. So this is both in the first mode, both of them are in phase. And in the second mode, we have M1 and M2. When M1 is moving in this direction, M2 is moving in this direction. So they are 180 degree out of phase. Again, when we come to here, if M1 is moving in this direction, M2 also moving in this direction. So 180 degree variation. So there are a node point that is considered fixed. Okay, and the amplitudes from here to here are half of the x and half of the x. Okay, here both of them are x1 of x. This is x1, x1. This is x2 from the reference position. They are the same. But here, this is x1 from the reference position, x1, and this is x2 from the reference position. Okay, so this is the representation, and this is the superposition of the two modes. We superpose in order to get general solution. We superpose the two vibrations. For the first mode, x1, x1. For the second mode, x2, x2. For 1 and the 2, for 1 and the 2. So this gives us these solutions. This is a general solution for. So how we can find, actually here by default, we understood that pi 2 and pi 1. Pi 2 is 180 and the pi 1 is 0. We understand it. But in general, how we can find these four constants? One constant here, second constant, third constant, means this thing, third constant, fourth constant. 1, 2, 3, 4 in two equations. We have two equations. One is this equation, another is this equation. So we have two equations and four constants. So we have to determine this from using initial conditions. So we have to derive this, the first differentiation of this, and the first differentiation of this will be implemented with initial conditions. Yeah. Sorry. Yeah. So we have to represent x1 of t, x2 of t, x1 dot of t is equal to 0, x2 dot of t is equal to 0. Conditions must be satisfied. Okay. So we implement this thing as we have discussed in the earlier portion. Okay. So this thing gives us this equation. Again, just considering this equation here, R1 x1 of 0 minus x2 0, R2 R1. Again, similar things. We finally find the equation of motion like this. Sorry. Sorry, this is because of my system. Anyway, so this is the final of our system of equation. Let me show you the four quantities. Which is because of stacking of the system, sorry. Anyways, let's be patient.